Hello everyone, I'm Josh, and today I'm going to be presenting on an application of Gaussian process regression to solve a problem for physics. This problem is fairly straightforward to understand. Suppose you're observing the motion of a tiny mote of dust, as small as you can possibly see, illuminated by bright light. If any of you have seen this situation before, you'll know that this tiny dust particle will appear to move about randomly. Now perhaps this dust particle is being affected by a consistent external force. This might be, for instance, a breeze in the room. This behavior is then governed by the Langevin equation. An interesting problem is this. From only recording the position of the particle at set time intervals, is it possible to infer this external force? If so, we can then integrate it to obtain the potential which drives this force, and this is a very important quantity in physics. It turns out that Gaussian process regression is one such way we can do this inference.
Firstly, for a bit of physics. The Langevin equation relates the velocity, which is denoted x dot, with the effective force experienced at a position x, f of x, and a random or stochastic thermal force, r of t. However, we don't actually have access to all possible positions x in a continuous manner. We only have a certain number of discrete measurements. As such, we would want to discretize this equation of motion using the Euler's scheme, which gives us this. So, after discretization, this Rn random force acts as a Gaussian white noise on the velocity with a variance that derives from several physical parameters such as temperature and the interval of our measurement, as well as this gamma parameter. These physical parameters are not very important for our purposes, and we will treat them as essentially known constants that we've predetermined. The next question is naturally, of course, well, what do the solutions to this equation look like? Well, something like this. Each of these colored lines are one possible trajectory of a particle. As you can see, it's fairly random, just like how that particle of dust was behaving. Our goal is this. From noiseless observations of position data, try to reverse engineer the forces. Visually, on the right, in black, we have these true trajectories of this particle. However, we can only observe it every so often at these red points. From this red position data, we want to somehow construct a picture of the continuous force function that generated it, as on the left. So let's get started. Our end goal is to get the posterior distribution of functions, given the training position data. As usual, all things begin with Bayes' theorem. We need to obtain a likelihood and a prior, which we can then multiply together to get the posterior. The prior is determined off the bat. We will use the usual GP0 mean prior with covariance given by a kernel function k. In this application, we elected for the Matern 52 kernel, which is a generalization of the radial basis function kernel. The simple motivation behind this choice is that spatially close points ought to have similar forces. Now that we have our prior, we move on to the likelihood. From the discretized Langevin equation, we can note that since our thermal force is a Gaussian random variable, our next spatial point x n plus 1 will also be a Gaussian random variable. We can work out an expression for its actual distribution as follows. First, we need to rearrange our Langevin equation to get it in terms of xn plus 1. Expanding it then gives this. We can then substitute our distribution for Rn, that is that Gaussian white noise distribution, and also introduce a delta spike, i.e. a distribution with zero variance on our constants for completion. Since this thermal noise doesn't depend on our position, these two are therefore independent random variables. Thus, using the usual rules for linear combinations of independent random variables, we can add the two, which gives us this expression for xn plus 1. Rewriting nicely, we get this equation. We can do this for every position data point we observe, which we can visualize as assigning a Gaussian in space for every data point as on the right. From here, we can then take the product across all our observed positions to make our usual multivariate data Gaussian. This expression for the mean is rather messy. It depends on previous x observations and not just the target force values as we would like. We can define a velocity as the difference in position points to simplify things. Also, we can assume that our initial position x1 is a known constant, which means that when we started our experiment, we released the particle from a predetermined spot. As such, we can drop the conditional dependence of our data on x1, which then gives us our likelihood at last. We turn next to the posterior distribution. Since this is a regression problem, we want to be able to predict new points. So rather than just this bare distribution, we want to look at the posterior prediction distribution. Let's start with the joint, which is just the usual GP regression joint distribution with the covariance defined as normal. Then, the conditional posterior prediction distribution will come from Bayes, We have dropped the constants here into a proportionality as they aren't required for the calculations. Now, this likelihood doesn't actually depend on the predicted f star values, and so it reduces to our original training likelihood in green. Notice that both terms on the right-hand side are known. The data likelihood, if you recall, is this. To make the product between this likelihood and the prior a bit simpler, let's rearrange things. Since Gaussians are symmetric with respect to the dependent variable and the mean, we can treat everything in this exponential argument as a variable, which lets us rearrange to make it explicitly depend on the force. Importantly, note that the underlying Gaussian distribution is algebraically equivalent. We have just shifted the terms around a little. The next step to evaluating this product is to make sure that the dimensionality of the likelihood and the joint prior match. One is n minus 1, while the other is n plus m minus 1. To fix this, we need to take the joint of the likelihood with the test predictions. These predictions are just numbers, which the position data do not depend on at all, and as such they are technically zero variance variables. For consistency reasons, we set the associated variance to small epsilon times the identity. Next, we can perform this product of two Gaussians using 8.1.8 of the matrix cookbook and properties of the block matrices. After this, we need to take the limit as epsilon goes to 0. This gives us at last the conditional posterior prediction distribution. Finally, we can marginalize this conditional we just obtained to give us our predicted mean and covariance, with these kernels defined the usual way. However, the rather familiar form of this solution is misleading. There are two very important differences. One, we have something that looks like the familiar noise term that we might have from having noisy observations, except we explicitly didn't have noise in our observations at all. What's the reason for this? Well, it turns out that it's mainly due to the second difference, which is that the targets that we are trying to fit actually come from our position data points and not from a separate label. And if you recall the Langevin equation, this naturally accounts for the mysterious noise term. Because each position update adds in this random thermal perturbation, it shows up in our velocity targets as a noise. Finally, we can put everything together. We started with noiseless position observations, from which we generate our velocity targets, fit hyperparameters, and then predict on new points. Finally, once we have this mean prediction for our forces, we can then take these functions and integrate them to obtain a guess of the underlying potential. To summarize very briefly, we have managed to go from observations of the position of a particle into an inference of the potential that this particle is being affected by, using some key ideas from Gaussian process regression. This wraps up my presentation. Thanks for watching.